Yeah, ladies and gentlemen, welcome to this 11th lecture on 3D coordinate systems. Today's topic is a maximum likelihood solution for the 2D similarity. So we have discussed how to describe motions and similarities, and we have looked into how maximum likelihood estimation in principle works. And now we want to look how this can be done in practice. Before we go to 3D, which will be then the topic in the next lecture, we will have a discussion on how the estimation works in 2D, and if we go back to 1D. So you all know straight line fitting from your first lectures on least squares estimation. I will repeat this in some way, but I will of course use this for that you get acquainted with the notation and with the principles which are behind these estimations of these similarities, which then transfer from 1D to 2D to 3D. In 1D and 2D, we have the advantage that these problems are linear in the parameters, so we have no problem just to take the linear Gauss-Markov model. And we assume that the data are Gaussian distributed. That means it is sufficient to use the mean and the covariances for describing the whole model. And we use the inverse of the covariance matrix as a weight matrix, so we can actually work with weighted least squares, which in this case leads to linear equation systems. So the principle here on this slide is how the linear Gauss-Markov model works. So we have a mathematical model which consists of the expectation of the observations which we collect in this vector. This is a linear transformation of our unknown parameters, and the dispersion of these parameters is the covariance matrix of these observations, which we will then specify in some way. Because we assume Gaussian distribution, we have to minimize this quadratic form where you here see the residuals L minus AX, which is the difference between our observations and the predicted values. And we weight them with the inverse covariance matrix with this matrix, which may be full or block diagonal or just a diagonal matrix. Now the condition for the solution for our x is that the partial derivative of this optimization function with respect to these parameters is 0. So if we take here the partial derivatives, we get here minus L times x transposed, so L minus AX transposed times W, and then the minus A. So we have here L minus AX transpose W, which is this part, and then the partial derivative of the second factor, which is minus A. So we have here the minus and here the A. So, and if you then rearrange this, knowing that this should be 0, we arrive at the what is called the normal equations, which is a equation system with a square matrix n, which is actually A transposed WA, which you see here, A transposed WA, and the right-hand sides, which are LWA, and here in the transposed form. So this would be the definition of our solution. In general, you will use this equation system and solve it. You don't need to multiply from the left with the inverse, so we write it down here. So we don't look at the numerics at this point. So this is the principle for the whole lecture, which is very simple and which you know from other lectures probably. So we start with straight line fitting. So what we have is a sequence of points in some domain t, let's say time, and they map to some domain which we call L, which are our observations. And usually you plot this in this manner. So you have a function L as a linear function of t. I plot it in this way because if you have here 2D and here 2D, we are not able to make such a plot because this would require a four-dimensional plot, which we cannot imagine. So this is a classical case of straight line fitting, and let us just start with that, what we know. So the functional model describes the relation between our observed values Li and the given values Ti, and it's a fine transformation R plus St. So we have the translation R and the scale S, and of course we have no rotation in 1D. We have capital AI observations, and we assume that all these values are real values. That means we can put them together in the observation vector, have this classical setup of our Gauss-Markov model. In this case, this design matrix, or Jacobian, is the 1 vector from here, because it's 1 times R, and this is I times, and here we have T times X, which is actually our S multiplied with all these elements of T. So this is the description of the Gauss-Markov model with this specific coefficient matrix. You see, I sometimes say coefficient matrix, sometimes I say Jacobian, sometimes I say design matrix. I mean always the same. The covariance matrix, in this case, we assume that all these observations are independent. That means the covariance matrix is a diagonal matrix with the variances of our observations, and that means 1 over the weights. That means also the weight matrix will be a diagonal matrix with the weights on the diagonal elements. So if we now build up the normal equations, we take A transpose WA, which is 1 transpose, T transposed, etc. And now we see here that we here at the 1 element, we get the sum of all the weights. Then we get the sum of the weighted T's. The same here, just reversed. And here we get the sum of the squares of the T's. So this is our normal equation matrix, 2 by 2. I come to these elements later, these blue indicators. And the right-hand sides are just the same coefficient matrix transposed, multiplied with the weight matrix, now multiplied with our observations. So we have here the weighted sum of our observed values L, and here the weighted sum of the products of the given and the observed entities. So this is very simple from the beginning. And now we want to make a little bit of an analysis. If you think of big systems, you usually try to get as many zeros in your normal equation system. So in this case, of course, it's not a big advantage, but it would be one, and we will see this. So let's assume we would be able to make this sum 0. What does that mean? That would mean that the sum of the distances of our T's from the origin is 0. That means we are at the centroid of all these data. Therefore, I wrote down this is proportional to the centroid of our T's. What is this expression here? This is the weighted sum of the distances of the T's to the origin. And if we take the average of all these, the squares, this is something like the average squared distance. And again, we have such a sum of the weighted observations here, which then represent the centroid of our observed data. So in the vertical axis, we have all these L's, and if the sum of all these L's is 0, we are in the centroid. So let's assume we work with the centroids. We see that this will be 0, this will be 0, so the normal equation matrix will be diagonal, and we will obtain a right-hand side for the first expression, which is 0. This has, if we do this, this has certain advantages. The first one, of course, the normal equation is diagonal. That means we don't have to invert it. We can just invert the individual elements. And we have even a very simple solution for the first parameter, which is the translation. And what we will see immediately is that if the t's are very large, then we will have a high relation between the 1, 1 and the 2, 2 element. That means it will be that this matrix might be close to singular, which we would like to avoid because we have to invert n, or at least solve the equation system with n as coefficient matrix. So let's have a look what the situation is. We have here our coordinate system t and L. We have here our observed data. That means the t's are given, the L's are observed. Now we take the center of all the t's, which let's say is at this place, and we take the center of all the L's, which let's assume it's this place. Then we will find out that this straight line which we fit passes through this black dot. So the centroids actually are the weighted averages of the t's and the L's. And now we would like to know what the average distance from the origin to all these t's are. And this is, so to say, the mean squared distance of the t's to the origin, which is the sum of the squares, weighted, divided by the weights. So we get an average distance, which we could say, if we would know the mean 0, then this would be a standard deviation. Now, as we have seen here, the d is approximately this value, and the tc here is this length. And one can show easily that this length is always larger than this length if the data are not at the same point. There's a nice proof in Wikipedia. So if you have T1, let's assume we have only 2 data, this is T1 and this is T2, then one can show easily from geometry that this is the arithmetic mean. That means that's our center, the mean of these 2 values. And this length from here to here is actually the mean squared distance. So you see from the figure that d is always larger than tc unless the 2 t's are identical. So this is what we will use. And that means the straight line fitting can be done in the centered model. So we start with calculating the centroids for the observations and the given data. Then we have the centered observations and the centered coefficients t. And that means the functional model now looks the following. We take the expectation of our observed data minus the centroid is some different translation now, plus the scaling of the difference between our given data minus the centroid. And if we now compare this, we find out that the original translation is identical to RC plus LC from here minus STC. So this is a very general relation which transfers to 3D, 2D, and we will use this in the following. So now, if we now have the straight line fitting with the centered coordinates, we get the same situation for the normal equations. Instead of having t here, we have the t's in the coordinate c of the centroid. So we have the t in the coordinate system centroid. And this leads to the normal equation matrix, which is diagonal, where we have here the sum of the weights, and here the weighted sum of the distances of the data to the centroid. So this is proportional to this distance. So let's assume we take the average distance of the t's with respect to the center. We get some deviation, and this is the dc, which we see here, which is, so to say, the standard deviation of the t's with respect to its mean. So for the right-hand side, we already have guessed that the first expression is 0, and here we get this sum of the products of the observed values multiplied with the given values weighted. That means we directly can write down the solution. The translation in the centered model is 0, and the scale, which has the same scale as before, is nothing else than the sum of these products divided by the sum of the weights. So we have a very simple algorithm, and so let's assume we have the algorithm, we have given point pairs LT, and the weights of these observations for capital I pairs of data. We calculate the centroids, we calculate the center of the coordinates and the parameters, and are finished. And we have seen in the graphics that the fitted line passes through the centroids, that means through this black point. There are other solutions which may be better if the data of T are also uncertain, then also this line goes through the center but lies a little bit different. Now, I said there's a problem in numerical stability. So if you have this normal equation system, 2 by 2, if it would be diagonal, the eigenvalues would be this value and this value. As soon as you have here off-diagonal terms, the eigenvalues are not so simple, and it may be that the eigenvalue ratio is extremely large. So you might have a very small eigenvalue, and if you want then to invert this 2 by 2 matrix, you may come into troubles if the minimum eigenvalue is too small. So we have to look for what is called the condition number. So the condition number of a square matrix is the ratio of the maximum eigenvalue divided by the minimum eigenvalue. So if the maximum and minimum are the same, we have the condition number 1. So this is the best value which we could get, for instance, for the unit matrix. And now in this specific case, it's easy to calculate the two eigenvalues because the eigenvalues of a 2 by 2 matrix, the calculation leads to a quadratic equation, and we can give these zeros very simple. And so the normal equation in this case is nothing else than the sum of the weights multiplied with the following simple matrix. So you have here the 1, here we have the center of the t's, and here we have the average distance, square distance from the origin. Now, if you take calculate the eigenvalues from this 2 by 2 matrix and calculate this condition number, you will come up with this expression. So you have here 1 plus d squared in numerator and denominator, and plus and minus the square root of this expression. You see here minus d squared, and here the tc. So now let's make a short argument how should be tc chosen. So let's assume that d is fixed. Then if tc is a large number, then the numerator will be large and the denominator will be small because you have a minus sign here. So it would be good to choose t, the centroid, to be 0. Then this ratio will be smallest among all others which have the same d. So for the given d, the centroid should be tc, and if we now assume that the centroid is 0, we go back here and see that this is a diagonal matrix, so we directly can see the eigenvalues 1 and d squared, and the condition number is 1 over d squared if d squared is smaller than 1, or is d squared if it is larger than 1. So in case of d squared is 1, then the condition number is exactly 1. That means we should choose the scaling of our data such that d is 1. Then we would get a normal equation system which has a 1 here and a 1 here and 0, 0, so it's a unit matrix multiplied with some factor. How do we get this scaling? The same way as we got the centroid. We shift, for the centroid, we shifted the coordinate system into the centroid, and now we scale the given coordinates such that the average squared distance to the centroid is 1, unitless. So if you have a range of, let's say, plus minus 10 meters, you divide all coordinates by 10 meters and get values around plus minus 1. So you work with unitless entities. And this procedure is called conditioning in numerical mathematics. And it's a very common way to guarantee that if you have large systems, of course in this case you will seldomly have a difficult situation, but if you have large systems, conditioning is really necessary. Conditioning actually means that you change the coordinate system of your data. So the first thing is we translate the data to their centroid. Of course, we do this for both systems, the given and the observed system. And we scale the data such that the distance to the centroid is 1, unitless. Then we perform our computation with these conditioned data and have some estimate. And then afterwards we undo this condition. That means we shift back and scale and come to our original result, which we would like to have. So when I say this is independent of the application, this way of conditioning you can do for probably all the problems which you work in geometry, and you should in order to be sure that you have no difficulties in numerics. You can imagine that even in our simple problem, you could have a bad situation. For instance, if you take as coordinates the Gauss-Krüger coordinates of data referring to the equator, which are in the millions of kilometers, in the thousands of kilometers, in the millions of meters. And if you have a small area, let's say 1 kilometer, that means that you want to have translations and rotation in this small area, and you refer all of these coordinates to a very far point, then probably this equation system will be extremely bad conditioned. So it's reasonable to work in the local system, which is anyway meaningful from a practical point of view. So let's go to the 2D similarity. There we have a similar situation. We have a data given now in the plane. Let's say here these 4 points in XY coordinate system, and we have here the X prime Y prime system with a translated, rotated and scaled figure. The dots are only for better visualization. We don't need those. So the task is, of course, if we have given these corresponding points here, to estimate the parameters of the similarity. That means the translation in X and Y and the rotation and the scaling. Now, let's lean backwards and remember that you learned complex numbers. Aha. So we make the same figure and just name the axis differently. So we keep the x-axis here, that's the real axis, and the y-axis we multiply with I, and each point then is x, has coordinates x and I, y, and we add them and have a complex number. So each complex number represents the position of a point in this or that system. And we know if we add complex numbers, this corresponds to a translation in the complex plane, and the multiplication with a complex number, remember, was a scaled rotation. So you take the magnitude of the complex number, this is a scaling, and you take the angle, then that means you get the rotation. So we use this and try to use the result from the previous section. So let's assume all the variables are complex numbers. So our observations now are Li is xi plus I multiplied with yi prime. That are our observations. Then we have the given coordinates x and y, which are now collected in ti, which are a complex number. The translation consists of the translation in x direction and in y direction, again a complex number. And here we have the scaled rotation, which is a complex number s, which you can either write in polar form with the length, the distance to the origin lambda, and the exponential of I multiplied with the angle. And you know from Euler's relation, this is lambda cosine phi plus I lambda sine phi. And we say this is S equals real part and imaginary part. And now you see what we discussed much earlier in this series, that you can write down the 2D similarity using only real numbers, namely A and B. And they are related to the cosine phi and the lambdas and the sine phi in this manner. So this is actually what we find out here in a very neat way. We assume isotropic uncertainty and have the following simple model. Our observed coordinates, complex numbers, plus the residuals, complex numbers, is the translation, which is a complex number with tx and ty, the scaled rotation s multiplied with our given coordinates. And this equation has weight wi. Now this looks exactly like the straight line fitting, and that means we use the result which we produced before, and maybe we need to take care that at some places we have complex numbers. So the model is expectation of L is R plus STI. With all these numbers are complex numbers now. That's the reason why I wrote down that these numbers are real values in the previous example. And the Gauss-Markov model now reads in the same way as before. So the coefficient matrix is 1, t. 1 are anyway real numbers, and the t's are now complex numbers, namely the given coordinates. And our unknown parameters are the translation r as a complex number, or translation in x or y direction, and s, which is the scaled rotation, represented as a complex number. So we have a very simple relation and transformation between the line fitting in classical manner in the plane, and here the transformation, the similarity between two planes. Now the stochastical model, of course, needs to have some care. So we assume that the real part and the imaginary part of our observed coordinates, that means the x and y coordinates which we observe, have the same standard deviation. So the covariance matrix of this vector is this variance multiplied with the unit matrix. And now there is a notational thing that we say the variance of Li is 2 times the standard variance of the individual coordinates, because we have x plus I, y. So it's the sum of these two variances. That means our stochastical model, that means the covariance matrix of our observations, is a diagonal matrix with 2 times the variances of the individual coordinates in complex numbers, or 1 over the weights. So this is very simple. And up to now we had no real difficulty in making this transition. Now we have to have a look a little bit before we go on. How is this relation between the complex numbers and that what we know from our normal real vectors? So let's have the first relation is the following. if we have a complex number S with a real and imaginary part B, we could put that into a vector AB. So this is actually our scaled rotation, which we could, if we would work with real numbers, put into this vector. Now, if we do the multiplication, S times T, we have A plus IB multiplied with X plus IY. And you remember it's AB minus BY. This is a real part, and AY plus BX, which is this part, the imaginary part. And you know that you can exchange the factors. That means the reverse product is the same. Commutativity holds. And if you now write this in matrices and vectors, you can do the following. We take this scaled rotation matrix. Let's assume this would be lambda cosine and minus lambda sine, etc. So this would be a scaled rotation matrix. We multiply this with our coordinates. Now let's see what happens. This leads to A times X minus BY. Aha, this is the real part of our complex number. And we have BX plus AY, which is actually the imaginary part. And you easily can see if we exchange these two factors, S and T, we get here the Z matrix of XY multiplied with S. So we have this nice relation that if you multiply the Z matrix of some vector, two vector with another vector, you can exchange the two the products. You could also, as we have seen here, represent a complex number by such a 2 by 2 matrix. So let's assume we have represented the complex numbers S and T with these 2 by 2 matrices. So we have A minus B, BA and X minus Y, YX. And we multiply them out. Of course, the first part, the first column is the same as we have did before. And now what happens with the second column? We have A multiplied with minus Y and minus B with X. So we get minus AY plus BX, which is the negative of this part. And similarly, we have B multiplied with minus Y and A times X. So we get AX minus B, which is the same as here. So if we do this type of multiplication with the Z matrices of two vectors, we actually have double the operations than if we would use complex numbers. So it might be useful to use complex numbers, because if we work with larger systems, we could save operations. Now there's an interesting link also to the transposed. So the transposed matrix is A minus B. So this corresponds to the complex number A minus B, which is the conjugate of S. And now this transposition transfers to complex matrices. So if you have a big matrix depending on two vectors, n, indexed with ij, and you transpose it, then you have to take the transposed of Z and exchange the indices. Now, if you do this for the matrix with complex numbers, n, with index ij, and you transpose and do the conjugation, which is called here, indicated here with the H, referring to Hermite, which was a mathematician in the 19th century, you actually have the same situation as here. So instead of having the transposition, we have here the conjugate transposition. So you could also say we first take the conjugate and then we take the transposed. If you try out this in Matlab and write down a matrix, let's say 2 by 2 with 4 complex numbers, A, and then transpose it, you will realize that the transposed not only does the exchange of the indices, but also performs the conjugation of the individual entries. And finally, we have the norm. That means the length of the vector S, which is a squared plus b squared. If we take z transpose times z, which is, because z is a scaled rotation, transposed is the square of the scale multiplied with the unit matrix. And this corresponds to multiplying the conjugate of the complex number with s, and you get a plus the absolute value of this complex number squared. So this is, so to say, a repetition of that what you probably learned in mathematics about complex numbers, and we will now use this. So we have the normal equation matrix. So we just make a small change by taking the A transposed here and replace it by 1 conjugate transposed, which of course doesn't change anything because the 1 is a real number. But here we get the conjugates of t. That means our normal equation matrix has, of course, here the sums of the weights. Then we have here the sums of the t's. And here we have the sums of the conjugates of our coordinates, weighted. And here we have the sum of the conjugates with itself. So this will be the lengths of the vectors, or the absolute value squared of these complex numbers. The same thing we have here. So we get here the sum of the conjugate given coordinates in complex numbers multiplied with the observed values. So this is the whole difference between the straight line fitting, which we discussed as first. And now we go to a centered model, and we do exactly the same. So we start with xy and x prime, y prime, and weights. And instead of working with matrices, we work here with these complex numbers. So xi plus iy is the first observation, etc. And these lines are exactly the same as for the line fitting. So we calculate the centroids, we take the centered coordinates, and then we actually get directly the estimate for our s, which is the sum of these products of the t's and the l's. Now we have to take care of the conjugate here. That's the only difference. And the translation in the original problem is nothing else than the centroid of the l's minus s, scaled rotation, multiplied with the centroid of the given data. And now if you want to reinterpret what is s, if you have s estimated, you just take the real and the imaginary part, and you get the a and the b. And if you take the real and the imaginary part of r, then you get the translation x and y. So the algorithm looks like this. Very simple. So you have a function which gives you the estimated parameters. And I write down here linear regression. And it works for real and it works for complex numbers. So we start with the L's. If they are real numbers, we have a normal linear regression. If they are complex numbers, we have a 2D similarity transformation. D indicates whether we have a 1D problem, that means a linear regression. And if D is 2, we have a 2D similarity transformation. And we specify the sigmas for the data. You have here written down the documentation. And what we start here is, of course, we first determine the weights, the individual weights, which are collected in this vector W. Then we take the sum of the weights. We take the centroid, which is nothing else than the sum of the t element-wise multiplied with the weights. And the same for the observed coordinates. Then we do the reduction to the centered data. Matlab allows such a simple form. So this is a scalar and this is a vector. This is allowed. And then we take the 2 element, which refers to the scale or the scaled rotation, which is nothing else than, and now you see here, the conjugate of the centered coordinates t multiplied with ct, element-wise, and element-wise with v. We sum up, and we get the estimate for s. this expression divided by the n2, which we just defined, and the translation is nothing else than L0 minus S, the center of the given data. And we put the estimates into a vector, and this is either a 2 vector with real values or a 2 vector with 2 complex values. So and this is then the output. So you see you have here a linear regression or a similarity in one program. Now let's go to the situation where we use real numbers. Why should we? Of course, we cannot represent such complex stochastical model with complex numbers. At least this is not very easy. So let's go to that what we would expect and use 2 vectors instead of complex numbers, and allow for an arbitrary covariance matrix per point. So we have an inhomogeneous and anisotropic uncertainty situation for our observations. Now you see we take the same list of definitions. Instead of having complex numbers, we have now, of course, the 2 vectors for the observed coordinates, the given coordinates, for the translation, and here the scaled rotation, which is this vector, lambda cosine and lambda sine phi, which is AB. And we have the anisotropic, the isotropic uncertainty. There should stand anisotropic. Yes. So we have the individual weight matrix, which is the inverse covariance matrix, which may have any form. Now, if we write this down, I start with this line. We have the given coordinates plus the corrections is the translation plus the scaled rotation multiplied with the given coordinates. So this is what we would expect. And if we write this in vector form, we have here the vector of the observed coordinates pair plus the residuals, the translation part, plus now we use these Z matrices of the vector S and multiply it with Ti. So this would be the vectorized form for each individual observed point. And we have a general weight matrix which has only diagonal terms for each point. So the points are uncorrelated. So with the model for the observations, of course, then is residual plus correction is R plus the Z matrix of this S parameter, which is A and B. And we use this immediately. If we write this down compactly in the classical form of a Gauss-Markov model, namely with the observations and nothing else than the stacked coordinates which we observed, the corresponding residuals. And the coefficient matrix now consists of 2 by 4 matrices. So the first part is a unit matrix 2 by 2. And the second one is the Z matrix of the given coordinates. Why? Because we have here Z of the scaled rotation multiplied with the coordinates. And we can exchange the product. So we can actually have here the product of the Z matrix of the given coordinates multiplied with the S, which contains the A and B. And the solution is just this expression, which is simple, and we get, of course, that what you expect. We get here the sum of the weight matrices now, 2 by 2 matrices. We get here the sum of the weighted elements of the given coordinates. So instead of T, we now have here ZT. And we have the same transposed here, and here we have the product of the ZTs of the given coordinates weighted multiplied with Z. So this is a straightforward application of our definitions of the normal equations, similar here. And now we again use centroids. Aha! We would like to have the centroids that this part gets 0. Then it would be numerically more stable. And we would expect that the rotation which we then obtain in the reduced model would be small. Maybe 0, maybe small. And then, of course, if we have the r estimated in the center coordinates, we can directly derive the translation in the original system, as we have seen. Now, there is a problem. The question now is it possible that we can choose centered coordinates Ti such that the weighted sum of this expression is 0? Is it possible? Do centroids really exist such that the normal equation matrix is block diagonal? Intuitively, one would say it should be possible. So, let's assume we want to solve the 2D similarity with isotropic uncertainty. We again start with our xy prime, the standard deviation. Now we, instead of complex numbers, of course, we have these vectors. The rest is the same as in the linear regression for the straight line fitting. And the estimated parameters can also be written down explicitly. So we have here the vector S, which contains the A and the B, which are then later lambda cosine phi and lambda sine phi. And we can get the translation in the original model from this relation, which we derived at the beginning for the straight line fitting. So the Matlab code is very similar to that. We determine the number of points, we take the weights, we have the sum of the weights, we take the centroids, we reduce the data, center them, we calculate the N22, we have a little bit more complex expression, a more complicated expression, I should say, for the S vector, and the T vector is the same here. You see here the Z matrix written out. And so this is also quite simple. Of course, the results using complex numbers or vectors is the same, because the mathematical model is the same. We use the same input data, we use the same model, scaled rotation and translation, and we use the same stochastical model. That means the results must be identical. If you implement this in Matlab, you find out that the solution with real numbers is approximately a factor 2 slower, which might be interesting or not. So what did we learn? So the 2D similarity can be interpreted as line fitting with complex numbers, slightly faster. The centroid coordinates which we should use lead to numerically more stable results. And generally we argued that conditioning of the data, that means translating them to a centroid and scale them such that the average squared distance to the center is 1. This leads to much better numerically stable solution. The centroid coordinates generally don't lead to a simplification. So if you just take a centroid, and we saw this in the last case with the anisotropic and inhomogeneous system with a general 2x2 covariance matrix for each point, then we are not able to find a good point at the beginning. Then, of course, the result is not really simplifying, though the translation vector will be only a small vector. If we take the simplified model, and now we know why we do this from the conceptual point of view, not because reality is following this. So because our mathematics tells us we should take this model, and if reality follows it, we are happy. If it doesn't follow it, we know what to do. This allows us to use centered coordinates, and it simplifies the estimation. And we will see that these results, to a large extent, transfer to 3D. And of course, later I will discuss how the evaluation of the estimates is actually performed. So this is today's lecture. Thank you very much. Next time we will look at the situation in 3D, which is a little bit more involving because it's a nonlinear model. Thank you very much.